Okay, so in the previous lecture, I have discussed in great detail the simple regression analysis, how you will construct a simple regression line in the Microsoft Excel, how you will interpret the results, how you will calculate correlation, coefficient of determination, and how you will check the hypothesis testing, how you will see, how you will check the p-value, is your hypothesis testing is accepted or your hypothesis testing is rejected. So Excel regression function have already calculated F statistic for you, and individually it also calculated standard t distribution for you, which is also called t statistic. So from the analysis, we in the last previous example, I have shown you that how you will run a simple regression analysis. So in order to extend the simple linear regression approach, in an example in which I will show you now how you will run a multi-regression analysis while using Excel. So before going to that, you need to understand multi-regression analysis. So multi-regression analysis, as I already mentioned, that in simple regression analysis, there will be only two variables. One will be dependent and another will be the independent variable. So in multiple regression analysis, the number of independent variable will be more than one. It will be 2, it will be 3, or it will be more. And we will check the dependent variable dependency on these independent variables. So once again, when you run the regression function while using the Microsoft Excel, it will give you separate results. For instance, it will construct an ANOVA analysis of variance for you, and in the other table, it will construct individual for each the relationship of each dependent variable with the independent variable. So I will explain that in the coming slide. I will discuss a very simple example. So in this chapter, we continue our study of regression analysis by constructing situation involving two or more independent variables. So now we will discuss how you will handle the data where you have more independent variable and there is only one dependent variable. So this subject area is called multiple regression analysis, which enable you people to consider more factors and thus obtain better estimate than are possible with simple linear regression. So I will also share you some research paper in which researchers use multiple regression analysis in which they construct hypothesis testing, and on the basis of that they interpret results while using some specific data. So multiple regression model. So as we construct the simple regression analysis in the previous lectures, so multiple regression equation that describe how the dependent variable y. So you can see from this equation, this is our dependent variable, this is intercept, this is my parameter 1. So slope of 1 for the first x1, for first x1 means this is independent variable 1, this is independent variable 2, and similarly if there are 3 independent variables, so it will be going on until the n or p independent variable, plus this is the error term, random variable, which is also called random term, and the mean of this error term is equal to 0. So that is why we not add this, but we generally in the equation format we just write it. So this is, it is just like before one, but generally when we write this, it will be before it was y is equal to a plus bx. So when we have one dependent variable and one independent variable. So for example, if we have two independent variable and one dependent variable, so it will be a plus b1 x1 plus b2 x2 and plus this is the error term. So normally we not just write it. So now how you will calculate these factors, because before we use some specific formulation for this intercept and for this slope, but now we have two slope. How we will calculate, because we have two type of data, two independent variable data, and we want to check the impact, we want to check the dependency of this on this and on this, and we also want to check this dependency at the both one. So in order to conduct this, in order to do this analysis, we will calculate these parameters while using different formulation. But Excel or SPSS or R, there are some built-in function which you can use in order to calculate these parameters. So I will show you very soon in a simple example. The equation that describe how the mean value of y. So this is my multiple regression line, the expected or the forecasted regression line. Normally we can also write it like this: a plus b1 x1 plus B2 X2. So when we calculate this parameter value and this intercept, when we put this, so after putting these X1, X2 values, we will be able to calculate the estimated line, the forecasted line. Estimated multiple regression, so they already estimated multiple regression equation is this. This is the estimated, the predicted, the forecasted dependent value. This is the slope. This is the parameter 1. This is parameter 2, and etc. etc. A simple random sample is used to compute sample statistics. So these are the slopes. Thus are used as the point estimate of the parameter. So you can write it as this way or it this way. So you not need to be confused. So now the question is how we will calculate these parameters. Normally, if we using manually, it will be very complex calculation. So we will use simple regression function in Excel in order to calculate this. So before going to calculate this, I am just going to discuss a very simple example. So this example is a software firm collected data for a sample of 20 computer programmers. So a software firm basically collect data for 20 computer programmers. So our sample size is 20. A suggestion was made that regression analysis should be used to determine if salary was related to the year of experience and the score of the firm programmer aptitude test. So now you can see salary related means salary depending on experience. So for example, if tomorrow if you go to some for some job, for some interview, they will ask you, you have some experience. So if you have some experience, so they will increase your salary. So now in this case, salary is depending on experience and the score on the firm programmer aptitude test, or if you get a good score in the test which they conduct for hiring a computer programmer. So if you have good experience or if you have a good score in the aptitude test, so now in this case salary, so salary is the dependent variable, this salary is the y, so we can write this y, experience is your x1 and aptitude test is your x2. So the year of experience, score on the aptitude test and the corresponding annual salary is this. For a sample of 20 programmers is shown on the text slides. So this is basically the data. As I already mentioned that salary depending on experience and salary also depending on aptitude test. So if someone have good experience and someone have good test score in the test, then they will give them a good salary. If they have no good experience, if they have no good test, so that they will definitely not give them a good salary. So now salary depending on experience and aptitude test. So this is the experience for 4 years. If this is the test score, the salary will be this one. If this is the experience and this is the test score, this will be the salary. So this is 20 computer programming sample data. So it starts from this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 and 10 is this one. So we have 3 different variables. So salary is the dependent variable. So you can write it. This is the dependent variable. So we will write this as y. This is let's suppose x1 and this is let's suppose x2. Now we want to check. So when we construct an ANOVA, analysis of variance, it will show us the hypothesis testing. That what is the scenario? Our hypothesis, the slope are accepted are equal to 0 or not equal to 0. Our variances are equal to 0 or not equal to 0. And then we will also construct it individually. We will construct a student tree distribution. So now, in order to construct this example, I am just going to show you that how you will run Excel, how you will feed this model in Excel, how you will run it and how you will interpret the results. So the most important thing is the interpretation of the result. Suppose we believe that the salary y is related to the year of experience x1 and the score of programmer aptitude test x2 by the following regression model. So the most important thing, you need to construct a linear regression model. The mathematical regression model, if you want to construct it, y is equal to a, or you can also write like this, plus b1 x1 plus b2 x2 plus this error term. Normally we not write this error term. So this will be your multi-regression analysis. Now you can see this is different from the previous simple linear regression, because now we have 2 independent variable and 1 dependent variable. Y is the salary, x1 is the experience and x2 is the program aptitude test. So y is annual salary, x1 is years of experience, x2 score on program aptitude test. So mathematically we can write it, this is y, this is our salary in 1000 or in 100, and this is the experience, and this is aptitude test. So now we need to calculate these things just like in the previous. How we will calculate B0, which is slow or intercept, B1, B2, and how we will calculate, how we will estimate the regression line. So now we need to calculate these, and R square mean coefficient of determination and the correlation and some other results. So in order to conduct this, I'm just going to show you that how you will construct this simple example in Microsoft. So you can see that this is the same data, which is mean the sample size is 20. So if you count it, you can see this count is 20. So this is that data, this is my salary, this is the experience, and this is the test score. Now we want to construct a regression equation. So how you will do? So once again, you need to check your tool pack. So just open this ribbon, option. In option, you need to go into add-in. Okay, this add-in will be open. So in this add-in, you need to go. When you go, you need to make sure that these are clicked, these check mark are filled. So these are fill mean we want the statistical package in order to do the regression analysis. So okay, then you need to we will feed data now in the model. So you need to click this data because we need to feed this data. In the data, you can see this is data analysis. So when you open this data analysis, there are different pack, ANOVA, correlation, covariances, but we are only interested in the multi-regression. So now you need to click this regression. So okay, when you click this, now delete this. Now we want, because this is, you can see this is the input y range, this is dependent variable range. So I am just only feeding the dependent variable. So this is my dependent variable. I just put it. Now I want to put the independent data. So we have two independent variable. So now you need to consider these two independent variable. If these are three independent variable, then you need to select all the three independent area. Because we have 20 sample now, so I just select those two independent data. Okay. Now the label, you need to click this label because I include the label name, salary, experience, and test score. And we want to run this test on a level of significance of 5%. Our confidence level is 95%. The output range, which output I want. You also need to click this residual. We want to calculate residual, standardized residual plot. Yes, I also want to check the residual plot line, the regression line plot, etc., etc. And the output range, where you want to sketch this, where you want to get the results. So let's suppose I want to get the results at this point. Okay, so just okay. When you put okay, these are the results now. So these are the results, and these are different plots. You can see these plots. Okay, these are different plots. Sorry, these are the plots which I will interpret later on, that how we will interpret these plots in the results. So these are the different plots. There are also some other plot option, but you can easily construct those plots very easily. So starting from the multiple R, this is my correlation. Correlation is very high. As you people know that when correlation is approaching to +1, we call that perfect correlation. Perfect correlation mean, so this is approaching to perfect correlation. So perfect correlation mean that the dependent variable behavior and the independent variable behavior are varying in the same way. If one is going up, the other is also going up. If one is going down, the other is also going down. And this is coefficient of determination. So in my previous lecture, I already discussed that what does it mean multiple correlation R and R square. Let me show you once again the definition of correlation and coefficient of determination. So you can see that correlation measures the strength of relationship between the dependent and dependent variable. Once a model has been developed and tested, the effectiveness of the model need to be determined. Correlation is used to determine how strong the relationship between the dependent and dependent variable. So now in this example, the correlation value is R is 0.91, which is very good, which is positive, which showing that correlation which showing that they have a strong relationship between the dependent. There is some strong relationship exists between dependent and independent variable, and it will be look like, when you sketch it, it will be look like this one. So mean it's approaching toward the positive correlation. Okay, the coefficient of determination value is also very high, so which show that a high value of R square, say 0.80 or more, would indicate that the independent variable is a good predictor of value of the dependent variable. So the coefficient of determination show that it's the independent variables, both independent variable x1 and x2 in this case, are good predictor for the dependent variable salary. So mean from this example it's clear that when the salaries, when the score in the test is very high, they will give you a good salary. So now they are behaving, they are moving in the same direction. In the other example, in the other independent variable, when their aptitude test, the score in the aptitude test and is very high, then the salary will also be very high. So in both these examples, it shows that this indicate the independent variable is a good predictor for the dependent variable. And you people know that a low value 0.25 or less would indicate a poor predictor. So I hope that you understand these results. Now I'm just going to show you some more results, how we will interpret those results. So the R value is 0.91 and R square value is 0.83. So both values are approaching to 1. So these both values showing that independent variable are good predictor for the dependent variable. Now in order to construct a estimated linear regression, in which we will put the value of x and we will forecast for the future values. So you can see these are the coefficients. These coefficients, I am just going to highlight these. These are the coefficient. The first one showing the intercept. So let me write the equation to you. This is my intercept value, and the other are the beta 1 or beta 2 value. So if this is the estimated regression line function, the estimated dependent variable, so a plus b1 x1 plus b2 x2. So a is 3.17 plus b1 is experience. b1 is actually the slope for this line x1, 1.40 x1, and beta 2 is the slope of test score. So test score is our another independent variable. So that is why we get two slope and one intercept. Intercept, this is basically the intercept of dependent variable y, and b1 and b2 are the slope of line 1. So line 1 will be for the experience data and line 2 will be for the test score data. So this will be 0.25 x2. Now if you want to predict salary, so let me put these value 3.17 plus 1.40 x1. So let's suppose x1 is 4. You can see this is 4. So x1 is 4. x1 is 4 plus 0.25 x2 is 78. So when you put all these values, you will get, so when you put x1 4 in this equation and x2 78, you will get 28.35. So these are our predicted salary. When you construct, when you put x1 value 7 and x2 value 100 in this equation, because this is our estimated equation, our predicted salary equation. So when you put this, you can easily construct this line. So these are our forecasted predicted values. So with this way, when you have more than one independent variable, you will construct, you will calculate coefficient like this way. You will put this in this equation and you can calculate the estimated line, regression line. So if you construct it, you can easily. So this is our expected line fit plot. This is test score line fit and test score residual plot, and you can also construct the regression line. So in order to further interpret the results, you also need to understand this ANOVA. ANOVA basically showing you the analysis of variance. In an analysis of variance, these are the degree of freedom for the regression. this is 2, for the residual this is 17, and 17 plus 2 will be 19. So I have already discussed these degree of freedom in the business statistic, and I will soon prepare some more lecture for you in the hypothesis testing in order to remind you these things. But now I will only discuss this significance value. So how you will understand this significance value? Let's suppose I'm just writing this, I'm just changing the format of this number, and I'm just putting this to 9. So you can see this value is 0.000000. So if I construct F statistic in this example, so it will be look like this one. So this is my F statistic. This one start from 0. Let's suppose the tabulated value of this one will be 0.00000023. Okay, and the calculated value is very high. So the calculated value is 42, which will be lie in the rejected region, and this is my accepted region. So we will reject our null hypothesis. Why? Because our calculated values lies in the rejected region. So if your null hypothesis that all the slope or the parameters will be equal to 0 or mean it will be same, so your null hypothesis that not all will be same. So from this result you can see that your null hypothesis is rejected. All the variances, all the slope or all the mean are not equal. Okay. If you want to further disaggregate the result, if you want to further interpret the results, we will calculate the t statistic for each individual. For each individual, you not need to be confused. For each individual mean, now you want to compare your salary, you want to relate your salary with experience. So when you relate your salary with the experience, so for this we will conduct a t statistic test. So these are the t statistic value, these are the p values. So you people know when the p value is greater than alpha. So now in this example we have already choose our alpha was 0.05. So when p is greater than alpha, then we will not reject H naught. We will not reject H naught. H naught means null hypothesis. In that case, the slope of intercept will be equal to 0. If I just write it, slope of intercept, which is A, will be equal to 0. H1 will be, it will not equal to 0. So now you need to check, you need to decide based on this value. You can see p value is very high from level of significance. So yes, we can accept H naught. This is okay. Now you need to check this. You can see this value is very, very low. This is very low than 0.05 because 6 times 0 then 188. So 6.0.888 means this is very low from this level of significance 0.05. So that is why the p value is less than level of significance. So that is why we will reject the null hypothesis for experiment, for experience related to the salary. Okay. Similarly, if you conduct a t statistic for salary with respect to test score is another independent variable. Our p value is 0.004. So 0.04 is still less than this value, which is less than 0.004, which is less than. So alpha is greater than p. P alpha value is 0.05 and p value is this. So this is still less than alpha value. So that is why we will p value when is greater than alpha, we will not reject H naught. When p value is less than alpha, we will reject H naught. So both. So now I already show you that how we will calculate these coefficients. These are the coefficient. This is the slope. This is the constant, which is slope 3.17. The experience slope is 1.4, which is our beta 1, and beta 2, which is the test score, which is the independent variable. So we calculate slope for two independent line, and this is the intercept for the dependent line. And similarly, we have already calculated, I already interpret these values, and these are the student t distribution. So now I will further interpret these results when you construct the estimated regression equation. I already show you that x1 and x2, and I already feed the values in order to forecast, in order to calculate the future values. So this is your estimated regression equation. Now, in order to interpret this equation, in multiple regression analysis, we interpret each regression equation as follows. So in this case, beta 1 represents an estimate that change in y corresponding to 1 unit increase in xi when all other independent variables are held constant. So for a specific time, we will consider that this beta, which is the slope of independent variable, which represent an estimate of the change in y. So y is your salary in this example. Y is your dependent variable in this example. So slope beta 1 will represent an estimate of the change in y corresponding to 1 unit increase in x when all other independent variables are held constant. So if I interpret this graphically, it will be look like this, because all other independent variable will be constant. So this will be y. So if we conduct this line, so you can see this is the change. This is the change, this one. Change in x, and this is change in y. So beta 1, which is now in this case is the slope of independent, which is the dependent variable, which is the experience in this case. So your first independent variable is experience. Beta 1 represents an estimate of the change in y. So this represents the change in y corresponding to 1 unit increase. So when this unit increase from this to this is change in x. So for this purpose, there will be a change occur in y, and this is the change when all other independent variables are held constant. So furthermore, in order to interpret this, because we have already calculated beta 1 is 1.40. So this is your beta 1, which is our experience in this case, which is 1.404 in that case. So beta 1 is 1.404, which we have already calculated while using the regression function in the Excel. So which show salary is expected to increase when you multiply this with 100. So salary is expected to increase by $1,404 for each additional year of experience. So you can see now this is comparison of salary with the independent variable x1. So your independent variable x1 is the experience. So the dependent variable, this we already calculate this slope, which is 1.404. When you multiply with this 100, so it will show that salary is expected to increase by 1404 for each additional year of experience when the variable score on grammar aptitude test is held constant. So because we will consider that the other independent variable is held constant. Similarly, beta 2. So we have already calculated beta. This is our beta 2. You can see from the Excel, which is independent variable slope, the coefficient of independent variable, which is test score. So score aptitude test score is another independent variable. Now we want to calculate this slope, and we have already calculated this coefficient, which is 0.25. So you can see this is 0.25, and this is the slope, this is coefficient of the test aptitude score, which is our second independent variable. Now we want to relate this to the dependent variable. So salary is expected to increase by, so this multiplied by 100 will be 251. So salary is expected to increase by $251 for each additional point score on the programmer aptitude test when the variable year of experience is held constant. So the other variable will be constant when you interpreting the results. So at this way you will interpret the results. So I have already explained this, that this is the sum of square, this is degree of freedom, and I have already explained this. Our p-value is 0.0, which is lower than the level of significance. So that is why we will reject our null hypothesis. When p-value is greater than alpha, then we will not reject H naught. In that case, we will accept H naught, and this is coefficient of determination. So Excel already calculated the coefficient of determination. If you want to calculate from the ANOVA table. So you can also calculate this from ANOVA table. This is the sum of regression sum of square. This is called regression sum of square, and this is called total sum of square. We have already discussed this sum of square in the hypothesis testing, regression sum of square and total sum of square. So in this case, the regression sum of square is 500.3285, which is this one, and divided by total sum of square. So total sum of square is this one, which is 599.7855. So when you simplify it, it will give you 0.8341. And while using the Excel, this value and the Excel calculated value is same, 0.83. R square value is 0.83. So you can see this is the R square value, which is 0.834. So simply you can easily calculate this value. So this is the regression sum of square divided by the total sum of square. You will get this value. I am just going to calculate this for you. This value divided by this total sum of square. So you can see this value and this value are same. So at this way you will calculate coefficient of determination, and I have already discussed the application of coefficient of determination, how you will calculate coefficient of determination and how you will interpret the result. So at this way you can interpret the coefficient of determination. Now adjust multiple coefficient of determination. Adding independent variable even ones that are not statistically significant causes the prediction error to become smaller, thus reducing the sum of square due to the error. So regression sum of square you can also calculate total sum of square minus error sum of square. When error sum becomes smaller, regression sum of square become larger and causing R square not to increase. So these are different indicators which show you that this way you will interpret your result. The adjusted multiple coefficient of determination compensate for the number of independent variable in the model. So R or Excel also calculate for you adjusted R square. Testing for significance is already discussed, and I already draw that in simple line regression the F and T status provide the same conclusion. So in the simple linear regression I discussed with you that from the p value you can decide accept or reject. In multiple regression, because in simple regression you have only one independent variable. In multiple regression you have more than one independent. That is why the F and T tests have different purposes. Because in that the T test we need in the multi-regression analysis to compare the dependent variable y with x1, and we also want to compare dependent variable with x2. That is why it has some different purposes. The F test is used to determine whether a significant relationship exists. So I have already shown you that is there any significant relationship. Would you need to accept null hypothesis or you not need to accept null hypothesis between the dependent and the independent variable? And for this purpose, we have already calculated R square and we have already calculated correlation coefficient. The F test is referred to as the test for overall significance. So I already discussed with you for the overall data analysis, because you have two independent variable, one dependent variable. On the basis of those results, we conclude that our F statistic is our hypothesis testing is rejected because the F calculated value lies in the rejected region, and our accepted region, the accepted region boundary is very small and the rejected region boundary is very high. So that is why we reject our null hypothesis, because it lies in the rejected region. We have already conducted test statistic. If the F test show an overall significance, then T test is used to determine whether each of individual independent variable is significant. A separate T test is conducted for each of the independent variable in the model. We refer to each of the T tests as test for the individual significance. So you can see this is the overall test, this ANOVA is the overall test, and on the basis of this we reject our null hypothesis that R slopes, R means, R variances are not equal. Why? Because this is the significance value which is very low and the calculated value is very high, 42, which lie in the rejected region, and this is our accepted region. So we reject the whole hypothesis. But because we have two independent variables, in order to interpret the results individually At the same time, we want to compare, we want to relate dependent variable with the experience, and we want to relate dependent variable with the test score. So for this purpose, we conduct t-test, and for this purpose, we calculated p-value. So this p-value is higher than level of significance, so we accept our null hypothesis for this. But for both independent variable, so these two are very important, but for both independent variable, our null hypotheses are rejected. All the slope, all the mean, all the variances are not equal. Okay, so in this way you will interpret the result. The same thing I have already discussed in the Excel, that for hypothesis testing, mean we will consider all the slope are equal to 0. So these are the slope, there is no intercept. Okay, and the alternative will be one or more of the parameter is not equal to 0. So one or more parameter are not equal to 0. And I already interpret, and how you will calculate. This is mean regression sum of square divided by mean error sum of square. So how you will calculate, I am just going to show you how you will calculate this calculated value in X. So you can see this is my F value, and how we calculate this. Let me calculate this value for you. Is equal to this value divided by this value. This is the regression mean sum of square, this is mean square. Regression, this is regression mean sum of square divided by the residual sum of square. So at this way you will calculate 42.760. This is the same value. So you will derive this value while dividing the regressor mean square divided by the residual mean square or the error mean square. So the calculated value, this is lie at this place in the rejection region, because if I start from 0, let's suppose this is my value, this is this value 0.0, this is, let's suppose, 40, so my value is 42, which is lie at this place in this region, and this is my rejected region. So at this way we will reject our null hypothesis. So all the mean, all the slope are equal to 0, one or more. So in our case, because this value is very high, which is 42 in this case, this is 42, and F alpha, the tabulated value, which is 0.000. So when we construct the F statistic, this is 0.000, our value lie in the rejected region, and this is our accepted region. So that is why our null hypothesis is rejected and our alternative hypotheses are accepted. We show that one or more of the parameter is not equal, all the slope are not equal, all the variances of these data set are not equal, all the variation, all the variable with respect to the dependent variable not behaving. Maybe one dependent variable with respect to dependent variable will be behaving in the same direction, maybe the other independent variable will not be behaving in the same direction. So when p-value is greater than alpha, so in this case our alpha is 0.05, so our p-value is less than alpha. That is why we reject our null hypothesis. Or if f is greater than this, where f is based on an f distribution with probability distribution function in the numerator and n minus p degree of freedom in the denominator. So at this way you can interpret the result. F test for overall significance. So as I already mentioned this, alpha is 0.05, degree of freedom which we have already calculated. You can see in the from the Excel sheet. You can see from the Excel sheet, this is our degree of freedom. You can see degree of freedom for this 2 and 17 and 19. And alpha we use 0.0. So alpha is 0.05, degree of freedom 217. F 0.05, this is 3.59. Reject H naught if p value is less than 0.05. Because if p value is less than 0.05, we will reject H naught. When p value is greater than 0.05, 0.05 means level of significance. So in this case, we will reject H naught. So F is greater than 3.59, so we will reject H naught. So in this example, our F statistic value is this one. You will calculate this value from the table. Okay, the F statistic table. In the F statistic table, you will check the value in the 5% level of significance, and the value will be this one. And our calculated value is F is equal to 42. So our calculated value is F is 42. and this is the tabulated value. So when you draw it, okay, the tabulated value is 3.59 and the accepted, the calculated value is 42. So 42 will be lie over there, which is in the rejected region. So that is why we will reject H0. Otherwise, you can also conclude this analysis with the p-value. When the p-value is greater than alpha, so p-value is, if this value is, let's suppose 0.6, the alpha value is 0.05. So we will accept H0. We will accept that all the slope are equal to 0. But in this case, our p-value is very low, as we already calculated in the Excel sheet. So at this way, we will reject that our p-value is less than level of significance. So we will reject H0. So this is just the interpretation of the multi-regression analysis. I will upload you some more material in order to further that you people understand the concept of multi-regression analysis. Thank you.